Good morning, everyone. Today is August 22nd, 2020. Been quite an exciting year so far. So let's see who we have here on the chat. Now, apparently I can take up to 10 people in the live room now. So what we have, so if you see that we have more than 10 people, then if you don't want to actually actively talk, then please go to our YouTube channel or our Facebook channel. But today we have with us Dennis Allen and Harry Ricker and Ian today. Bright and early with us in the morning. We also appear to have Dr. Bill Lucas on Facebook. Bill, you should come join us live. We always love it when you're here. Okay. So let's get on with the questions we're having today. So I see, yeah, we have Harry here. So right early in the start of the meeting there. So let's start with Dennis. So how are things going in your world, Dennis? Have you come to any world-shocking conclusions this week?
No, not this week. No. Still.
Now, last week I announced the shape of a photon. See, so I'm looking for stuff like that, right?
I beg your pardon?
Last week I announced the shape of the photon.
Oh,
I
didn't participate last week. No, I'm sorry.
Oh, well, you missed my important and exciting announcement. I could write a paper or make a video or something. I said that the shape of the photon is similar to a rod. So when it travels through space, it's literally something like that. It's like a rod, and the polarization just depends on which way the rod is rotated. So it could coming at this way or coming at you that way. But for a photon, which is generated by atomic electron processes, that is the actual physical shape it would occupy in three-dimensional space. It's something like a rod. It's still a compression wave effect, but it's restricted in that dimensional. See, I also mentioned that we have that whole wave-particle duality, and it appears that when you're at the high end of the frequency, like gamma rays, everything looks totally like particles. But if you're at the very low end of the frequency, like radio waves, everything looks like waves. And that's because I think there's this other very, very big difference between radio waves and light waves, which are generated around atoms. So that's what I call atomic light. That's because it's generated in these rod-like structures. But radio waves are more like ocean waves, which are very, very large and wide, and they can have any amplitude. So that I'm calling out a very, very large structural difference between what's a radio wave and what are light waves. And that's why we see this particle-like behavior at the higher frequencies, but the wave-like behavior at the lower frequencies. You got some.
Franklin, what does magnetic photon look like?
Oh, well, you were asking about that last week, so I think that's still an important question as to whether the magnetic field acts as a photon. So I would say no. I would say that the magnetic field, it acts as a geometric geometric property of space. Like I said, I tried to explain it last time as saying that you're in a field full of flags. You're in a field full of flags, and you throw balls at the flags, and the balls get deflected because it's hitting stuff in space. But technically, the thing which is still doing the deflection would still be the electrostatic force, because that's really the only thing you have available. So essentially, the photon of the magnetic force eventually ends up being basically the same photon that causes electric charges, which is literally still a wave. So to strictly answer your question, the photon of the magnetic wave, which is the thing which is actually causing the force, is actually completely identical to the photon which causes the electric charge, is what I would say. But it works due to a different geometric effect. That's
well, Frank, if what you say is right about radio waves and light being different, how do you explain the fact that the electromagnetic spectrum seems to be continuous, all the way from very long waves that the Navy uses to communicate with nuclear submarines that are submerged, to the extreme high frequency? There seems to be a continuous spectrum. So where does the waves take over and the particles leave off, or vice versa? What's the cutoff line?
Well, I'd say the cutoff is due to our physical ability to generate things like radio waves. So as soon as it gets too high in frequency, I mean, maybe Harry can speak to this. It's like, can we create a radio wave that is actually at light frequencies, right? I'm thinking that that's probably the problem. It's like, what is the highest frequency that we can generate a radio wave at? And where does that lie in relationship to electromagnetic spectrum? Because it's like, yeah, as Dennis says, there is this continuous spectra. But I would say that at some point, where is that cutoff, right? That cutoff is a technological limit based on like how fast we can get electrons to oscillate in our circuits. But I don't know. What is the maximum?
You're asking me for an answer?
Yeah, Harry, I wanted to know, what is the maximum usable radio frequency, and where does that fall in the general electromagnetic spectrum? We can't transmit radio at light frequencies, can we? Or can we? I don't know.
All right. Well, that's kind of ambiguous. I think the answer is that the electromagnetic spectrum consists of the same things, from the low frequencies to the very high frequencies. It's described differently at the different frequencies, which is the source of the confusion. Because they have a model of a photon at high frequencies, light, for example, and gamma rays, another example. And then there's a different model at the lower frequencies. So we're really talking about two different models, and which model do you want to use? I think that you could talk about photons at radio frequency, because that's not really where the model is supposed to be used. But that's kind of being, like what a physicist would say. It doesn't really answer the question fundamentally, what is a photon or what is a radio wave?
Well, that's what I'm trying to answer, and that's what we're trying to get at, is what is that difference? Because there seems to be quite a difference in behavior. So that's what I was predicting. I would predict that there should be some hard limit at the maximum frequency that you can use for radio waves. What I would like to see is, I'd like to see someone have an antenna and have it generate frequencies at, say, the red light frequency, right? Which is like, I'm not exactly sure how you would, it's like past the terahertz range. It's like, past ultraviolet. Well, it would be.
Electron lasers wiggle electrons to get visible light.
Yeah, and light is always generated around an atom due to electron transition, right? So that's a very different way of generating an electromagnetic wave, say, coming off of a radio antenna. Generating a wave off a radio antenna is actually relatively simple. You just create an oscillating circuit that changes the voltage, and you attach it to a piece of metal, and that generates radio waves. And you're only limited by how
Well, it's
fast
not
you
as
can
simple as that, Franklin.
It's not? Is it more complicated than that? I can build a radio transmitter
Well,
with
you
my
have to have the
101
piece of
radio.
wire, that you're talking about that you just dismissed has to have a certain dimension, and the dimensions of the wire have to be related to the frequency of the oscillation.
If you want to make a good sensitive, if you want to make a good sensitive radio transmission and receiver, yeah, we tend to do that. Although, like the crudest.
Well, I wouldn't recommend that you try it, and without doing it the right way.
Yeah, I mean, like I said, I have my 101 Radio Shack projects kit, and you can build an AM radio transmitter, and they just tell you to hook it up to the big wire that they give you, and yeah, it works. So it doesn't work very far, but certainly it works. Certainly it generates a radio wave. And that's all my point is, that it's not that complicated to generate a radio wave. You just put some electricity in some wire, and you'll get something out that travels a distance.
Well,
Actually, I'm kind of surprised that the earliest radio transmitters had to use like these spark gap things. Basically, I think they had to do that because they just need to get the maximum amount of power out into space, and they really didn't care about frequency selectivity or anything. They just wanted to dump out massive amounts of energy into space, and so that an equally crude receiver could receive it. Right? Initially when they did radio, there was only one frequency, right? And if other people were on it, then that would interfere, and you couldn't, someone trying to send a SOS and someone else was like sending the daily news, you probably wouldn't hear it because those two things would collide because there was no frequency selectivity. Right? Then I got smart and figured out how to encode the signal onto a single frequency, and then we could use resonant circuits to pick out just those frequencies out of all the noise.
All right, you're almost there, Franklin. But the difference between radio and an atom is that in the case of a radio antenna, the dimensions of the radio antenna are defined in such a way that the oscillations take place at the frequency that you're using, the radio frequency that you're using. Now, what happens in the upper frequencies where we're talking about light and photons, the photon is supposedly the quantum of energy that is necessary for the oscillation to take place in the atom. So the photon, I'm not really sure that it's a thing or an object. It's just a definition of quanta of energy. So is it really a thing, or is it just a model object that allows them to describe what happens in an atom when it oscillates?
Well, I'm saying that it is actually a thing. That's the significance of what I announced last week, is that I'm saying it's actually a physical thing. If you had a microscope,
so it's not a concept, it's actually something that exists. So how does it exist? What is the parameters that define its existence?
I explained that I believe that the physical shape, the volume it occupies, is a rod, right? That is what I'm saying. If you were to look at a physical picture of a photon going by, if you had a sufficiently powerful microscope, that's what you would see. You would see something that goes through space, which is approximately the shape of a rod. I'm not exactly sure what shape it would be, but it would have to be something which is much longer than its actual width. So it's going to be like a rod. I think that explains, why the energy that comes out of these electron processes is actually quantized. You do have to explain that. Why is it that we have this?
So the idea of a wave packet that the physics books talk about is wrong then?
Well, it is a wave packet. I'm just saying what the specific shape of that wave packet is. Although I don't know exactly, how wide it is exactly, exactly how much space it occupies. But I would say it is a wave packet. I would say that when an electron transitions it goes up and down. I mean, this is what it causes. It's basically like dropping a bowling ball on your foot. So that the higher that you drop the ball, the more energy it impacts your foot. But instead of your foot being there, it's like a bell that's there, right? It's like, it's like someone hitting the bell, bing, and every single time, the bell resonates and goes back and forth. That is what's sending out these photons. Now, I'm not exactly sure how the atom does that, but I'm figuring it must be the same thing that happens when positrons, electrons annihilate, because that's also two particles hitting each other, and there's just a single resonance in that case. But the problem there is that you figure that there has to be at least two photons being released to determine what the frequency is, at least two. It can't just be one. If it was, one wave, that doesn't have you would just register the quanta of one energy, and that would be it. But so I'm thinking that it has to ring when these electron processes are happening. It does have to ring at least twice, maybe 3 times, enough so that there is a frequency that you can detect. So it would be like the more energy you put in it, the faster it rings, kind of thing. So I'm not exactly sure how that would work. Typically, resonant frequencies are all the same no matter how hard you hit it, but somehow it's more like if you threw a tennis ball into a box, and the harder you threw it, the faster it would go and rattle around in the box or something like that. But yeah, I mean, it's a very good question. That's why I tried to answer it, which is, what is a photon? What's its shape? And so I think that that's a fairly simple shape of a rod. And I think that that's something that experimentalists could actually look for. Because I'm saying that the polarization has to be encodable upon that. So that's why it's important that it be a rod, because a rod will be able to, as long as it's traveling perpendicular to its direction of travel, then certainly it can encode any polarization direction you want, right? So that's the important things that you have to encode. You have to encode that it's a specific amount of energy, and you have to encode that it's capable of carrying the transverse polarization information. So the simplest thing that I could think of that could do that is a rod shape. So
until we have the experimental results with respect, it's really speculation, as to whether these things are real entities or whether they're just useful models. But just getting back to the early radio transmissions, using a spark rather than a continuous wave. It's a bit tangential, but it just reminded me of it when you were talking about it. In the very early days, before continuous wave reception, before the semiconductor diode, or even before the cat's whisker, they used a piece of apparatus called a coherer, which basically had metal filings in it. And when you received information, well, these filings cohered together, and you got a signal. And unfortunately, when the signal stopped, there was a hysteresis. Well, in fact, the filings stayed together, so you needed actually to tap them. You had to have an electromagnet to tap them to disintegrate them again. Now, I was looking at this recently, and the physics books say that the operation of these coherers is actually not really understood properly. It's a bit of a mystery. So I was wondering if anybody had anything to say about that.
Well, I know Harry, he sent me an article about the magnetic...
I looked into this. Into this, and I talked to my brother about this, who's a metallurgist. And I don't think they really understand the physics of this. But the idea is, as I understand it, is when the signal is present in the antenna, okay, there's a current that flows through the coherer, and
Yeah.
that creates magnetic fields in the particles that want them to stick together. And when that happens, the current or the resistance between the particles is reduced. But if you think about it, that sort of asks your question: how could there be a current in the antenna if there's no current through the particles, and the current through the particles is what causes them to cohere? So that's kind of a chicken and the egg problem. So nobody that I know of is actually working on this because it's not really a current physical problem. But, it's kind of mysterious. I think you're right about that. Does that help you
It's an
answer?
interesting example of how practical engineers got things working without really understanding the initial principles, behind them. They just got things to work, without considering too much about the theory. If you're wondering about the theory, you probably would never come to a practical realization of it.
Well,
I think that's effectively what we're currently doing, right? Like right now,
discovered
the radio
is doing experiments with detecting electromagnetic waves. And kind of my thought is that there's a pretty intense electric field. Spark hits the antenna. Okay, the wave field, and I think there's an intense electric field, and I think that electric field is pretty high, and that is what causes the current to pass between the particles. Does that make sense to you?
Well, yes. I mean, first you were talking about the magnetic effects, Harry, and now you're talking about an electric field. I can accept in principle any of those.
You have two problems. The first problem is the first thing is the principle of the detector is that if there's no electromagnetic field, the resistance of the circuit is high. Okay, so a battery connected to this detector. Okay, and there's no current in the circuit. Now remember, there's a battery and a relay. Okay, and then this coherer device, and that is a high resistance. Okay, it's in a high resistance state. When the EM wave arrives at the antenna and presumably passes through the detector, the coherer device, the resistance in the circuit of the relay below resistance, and the relay closes. And that relay is used to activate a printing device. Okay? You understand what I'm saying?
Yeah, that's how it actually works. It's more the underlying.
Hold on. When the relay closes, it activates the tapping device, which hits the coherer detector, hits the particles, and causes it to go to a high resistance.
That's right.
Okay?
Yeah.
But if there's an electromagnetic wave present, a high resistance goes to a low resistance. The circuit continues to conduct electricity. So it has to do with the lag time between the tapping and you understand what I'm saying? There's like a time constant of the circuit. So the relay doesn't actually open when the tapping device taps the detector. Do you understand?
Okay, but that's a detail, I suppose, Harry. It's
No. It's real important because what happens is when the electromagnetic wave is not being received, when the tapping taps the detector, there's no electromagnetic wave, and the circuit opens, and the device which printing on the printer stops, and it stops printing on the paper. Okay, So if you think about it as a mark on the paper, it will have a long mark on the paper and then it will stop printing.
Yeah, I'm looking
And
at
the
this,
difference
the
between a
Wikipedia on this coherer.
Please, Frank, don't confuse us with what Wikipedia says. I'm trying to explain it, okay? Did you understand that?
I think that's
I mean, I understood the description of it, but I'm actually more concerned at the moment about the fundamental principles governing the operation of the coherer itself, how it moves from a state of non-conduction to conduction, albeit through a time constant procedure.
Ian, could there be something involving the van der Waals force that's keeping it, when all those particles in the, what you call the condenser? No, the coherer. The coherer are forced together, and then that force is removed, the particles stay together. Could that be a van der Waals type force?
Well, that's a new proposition, Bob, and I'd have to give that some thought. It very well could be something to do with the internal forces within the particles, the van der Waals force, as you say. I haven't seen that described anywhere, actually.
Yeah, this is new to me. I've never heard of them actually receiving radio signals this way. So this is interesting because I thought maybe this had to do with, say, magnetic particles or something, but I don't know. Apparently not. Apparently you just have these metal, like little rods, which are in the
filings.
Yeah, they're like filings.
They're filings.
And what happens is that when the radio wave, yeah, there's like these little elongated metal filings. And when the radio wave comes along, apparently they all line up, and then that causes a short to go through the circuit, and then that rings a bell. So, and then that they know, aha, I've received a radio signal. And then it just stays that way just because of gravity. I don't think it's van der Waals or anything like that. What's more interesting is that when this thing receives this massive wave of random radio frequencies just dumped into the space, they align. I was reading in the article here, maybe that's due to static electricity effects. Like if you charge up, stuff, they'll all kind of just like line up. Like put your hand in the Van de Graaff generator and like, your hair just lines up, goes straight out, or something like that. Not exactly sure, but that was speculation there. That something is happening which causes the particles to be charged. I mean, I can imagine that if you're talking about like a little metal filing that's like a rod or something like that, we know that when the radio signal comes in and hits any metal and gets absorbed, we know that electrical current will be induced somehow, right? And once you do that, presuming that you get a positive and negative end in this little rod, then you could conceivably think that they would align to each other so that the positive would face the negatives. So that's the only mechanism that I can think of based on just my initial encounter with this phenomenon and how that would work. So my hypothesis is the radio wave comes, it generates this slight electric current that causes one side of the metal filing to be positive, the other side to be negative, and then that causes electromagnetic forces to cause the particles to align, and then all the aligned particles allow the big current to flow to ring the bell. And then to stop ringing the bell, you have to randomize all the particles back to their original random position, so that doesn't provide a very low resistance path to ring the bell. That's my hypothesis. Could be wrong. I don't know, but this as much as I could think of at the moment. What do you think, Ian? Is that the way it works? Is that solve the mystery?
Well, I'm interested, Franklin, in that we're debating whether the fundamental cause of the coherence is electromagnetic, is electrostatic initially, is magnetic, or indeed is more mechanical, dynamical. And we can postulate all these things, and we don't seem to be directed in any particular direction by the established knowledge. Whether
that's why I would say. No, I'm saying it's electrostatic.
My own view is that it's probably electromagnetic, which let's say includes electrostatic. It probably is of that nature, but I'm not quite sure exactly how it manifests itself. Your hypothesis is conceivable, but I don't know what we really ought to be doing to home in further on this question. Whether we can just speculate and talk about it, or whether we need more experiments, or whether theory can actually lead to the results. It is rather academic, of course, because these units are not used anymore. Once we have continuous broadcasting, we use sophisticated semiconductor detectors and so on, and we have modulation and super heterodyne circuits and all that. This is gone. It's gone over 100 years ago. But it is an interesting.
Well, Marconi went to the magnetic detector, which I've sent to Franklin on a number of occasions, in which the iron wire is drawn in a solenoid that's connected to the antenna. So there's a magnetic alignment created within the wire that is detected by the detector.
Well, I mean, that is a more
and
obvious.
That became, I think, went into use at the time of the Titanic and that sort of thing. There are other people invented other detectors, a detector. There were a lot of different kinds of detectors, but the one we're talking about, which is the coherer, was actually the first detector that was used, and that was used by Marconi in his very early work prior to 1900.
Yeah, it's a very simple setup. Let me just show you.
It was possibly invented, by Brown or maybe by Lodge, and it was certainly used by Marconi later.
Yeah, so here's a picture of one of these things. So very simple. They're probably putting power on one end here and putting a bell on the other, and in between here, in this little gap here, are a bunch of metal filings. And finally, when the radio wave is received, it shorts these out. Very simple principle of operation here. Now, the other detector that Harry was talking about, so he sent that as an example of possibly something which receives the magnetic waves. And so I was challenging everyone to show me something that detects the magnetic wave as it travels through space. So Harry sent me that.
You said there's no such thing as a magnetic field in an EM wave, Franklin.
Well, definitely
you said there's no such thing as a magnetic field in EM wave.
Well, definitely there's an electromagnetic wave. Well, there's an electric wave, and there can be but we actually have an electric field, and we have a magnetic.
You said there's no magnetic.
Yeah, I'm saying that when a radio wave passes by, I'm saying that there is no electric field and there is no magnetic field associated with that. That is my hypothesis. And once again, my hypothesis could be completely wrong, and that completely disagrees with everything that mainstream says, because mainstream says.
I don't see how this Branly detector could possibly have worked.
You're talking about the coherer? How that worked? I mean, the coherer doesn't work regardless of what you think is going on, because I don't think either magnetic.
According to your
magnetic
theory, this
field-
Bramley detector.
Go ahead, Harry.
Well, Franklin, I think this proves your theory. It's completely wrong.
Well, it could be. I mean, you know, that's why I discuss things. It could be. Why would it be?
You don't have
You know?
electric and magnetic fields in your theory, according to what you just said.
Yeah, there are no electric fields and no magnetic fields in the radio wave. There's no such thing. That's my hypothesis. And that all these things that we're seeing in radio reception don't have anything to do with, say, induction. I mean, that's the one thing people argue back and forth. They say that you're getting the radio signal because of the induction from the magnetic field. And then other people say, no, you're getting the perception because of the electric field, which is polarizing the antenna. You know, and I'm saying that it's, you know, like make up your mind, guys. Is it the electric field or is it the magnetic field that's causing the signal? You know, maybe it's both, but I'm saying that it's neither. I'm saying that it's a literal push and pull, like a speaker hitting a microphone receiver. That causes a physical vibration in the receiving apparatus. And that is what I think the radio wave is. It's similar to a sound wave. It's a physical particle A hitting particle B, causing it to vibrate back and forth. It's not due to magnetic induction, nor is it caused by an electric field causing the antenna to become polarized. That is my hypothesis. So that's why I was challenging people to send me evidence that when you are transmitting a very strong radio signal, that you should be able to detect the very strong electric field and or the very strong magnetic field. Now, you did send me that link, that very interesting link on Amazon. You know, they have a detector that can detect all three kinds of fields separately. So I can detect the radio field, it can detect the magnetic field, and that's measured in milligauss. So Gauss is good because Gauss is what you measure magnetic fields with, and the electric field, which is measured in volts per meter, right? So, you know, I wanted to go and take that meter and go up to one of my television transmitting towers, which is transmitting at like 15 to 20,000 watts, and go see whether what you can measure. I mean, do you see a high electric field around those transmitters, or do you see a high magnetic field around those transmitters? Certainly, the radio frequency part of that meter is going to go crazy, right? That's going to take that meter there. But if my hypothesis is correct, I would predict. I haven't done this experiment, but I would predict that you go take that meter up to this very powerful radio transmitter, and you would find very little electric field, and very little magnetic field. And this meter is capable of detecting the AC fields, right? It doesn't need just a constant single polarity field to detect. I mean, certainly these would be AC fields. So certainly if there is any instrument capable of detecting the separate electric and or magnetic field, that would meter would hopefully be able to do it, maybe. So, but I don't know. So, you know, and if all three levels spike, then well, then maybe you have to eat crow. You know, it's like, okay, well, I guess there's a big electric field here, and there's a big magnetic field there. But I don't. I'm guessing not. I think you put a very sensitive like compass up to these radio receivers, and they probably just still align to the Earth, right? You probably wouldn't even see it vibrate. I'm guessing, because you'd have to have very sensitive compass. But that's the level of experiment that I'd like to see done, right? I mean, I could be wrong, and I could be totally wrong, right? But I've just felt that it doesn't make sense that we have these electric fields that can propagate for like billions of miles.
Franklin, about the compass. They're deliberately damped. Okay, so they don't
Yeah, they're
move
deliberately
around.
damped, so it wouldn't be a
They're
very good
deliberately
detector.
damped. They have they have the magnetic damping, or they're placed in a
Usually liquid
fluid
damping.
or something that prevents them from oscillating around. So what you're saying is the compass is designed to prevent detecting what you say you want to detect with it. That
Yeah, so
doesn't
that's
make
why
any
you wouldn't
sense.
want to use a compass. Probably you would want to use one of these ultra high sensitive, ultra cold squid magnetic detectors, which are apparently super sensitive and wouldn't have any kind of damping or whatever. You definitely want to use something like that. And it was only
I don't
sensitive
know.
to
They
the
may have
magnetic field.
filtering in them to prevent being activated by electromagnetic fields.
No, I don't know that that's the case. I mean, they generally speaking don't use your compass next to large radio transmitters. And even if they did, it's an AC
Well,
signal. I don't see it.
I think we know that trying to detect an electromagnetic field using a static magnetic field detector is not correct application for the purpose.
Yeah, but probably because it doesn't work. That was my hypothesis. Is that if you were
Yeah, right.
looking
Okay.
for, I mean, you do see these things around radio transmitters. You know, and they wrote them off because they say that the electromagnetic field here is higher than is recommended by OSHA, whatnot. And I imagine if you took this detector and you put it right up against the radio transmission feed cable, that would show a very high electric field because there's a lot of electricity running up and down on that thing. So at very high voltages. So I would think you would see the electric field there, but that field would drop off quite rapidly as you left the area. So maybe
Well,
just
it
like
depends
5
on the
feet
type
away,
of
it'd be like
antenna,
0.
Franklin. I mean, you're making a statement about I'm going to do this with an antenna. What kind of antenna? There's lots of different kinds of antennas. There's antennas which operate at high voltages, which are open circuit antennas. There's closed loop antennas, which don't generate high magnetic fields. So, I mean, what kind of an antenna are you talking about? I mean,
I'm talking about a commercial television transmission tower.
You're just throwing out, blah blah. You need to. I mean, I don't know. I just tell me what kind of an antenna. Give me a specific kind of antenna that you're talking about that you want to do.
A commercial television broadcasting antenna.
This experiment with devices that are not designed to detect the fields that you're denying that exist. So I just think this discussion is kind of pointless.
Are you listening to me? I'm saying commercial broadcast television tower.
Yeah, if you go with a device designed to detect radio frequency waves and it's transmitting, you're going to get the needle to go to the pin if it's transmitting a lot of power.
Yeah, so that's obvious, but what will the electric part of the meter register and what does the magnetic part of the meter register? That's the question. If mainstream is correct, then those should also both be paid.
Depends on the meter.
Well, maybe. I mean, I'm kind of wondering how this meter works. I mean, it's supposed to be able to detect AC waves. I mean, is it really doing that? Or is it just what? I mean, where else do you get an AC, say, magnetic signal from? Right? Well, maybe you get that from a transformer,
well,
right?
You'd have to get the manual for the device and look at the schematic and see if they are willing to divulge to you how the device works. Sometimes they don't want to do that.
Because I would test this I would go take it and put it next to my Sonicare toothbrush, which charges by magnetic inductance. So if I take that meter and I stick it next to my Sonicare charger, then I should see a very, very high magnetic field, right? So that's one way to test to see whether this thing actually measures a magnetic field. So definitely that's a changing magnetic field. That's basically an open transformer. And
Depends on meter and how it works. Does the meter register frequencies at hertz, which is the frequency at which your toothbrush operates? I don't know. To specify the meter can detect waves at that frequency or not. I don't know. You'd have to look at the specification for the device and the engineering manual for how it's to be used.
Yeah, that's absolutely true, because I kind of have my doubts as well as to whether this thing does actually measure the magnetic field or measures an AC electric field. I'm not sure how I'd get an AC electric field. I mean, I suppose it should detect the changing electric field in just an electrical socket, I suppose. If I stick it into an electrical socket, we have a voltage.
If you put a meter in proximity of a high voltage transmission line, you'll obviously get an electric field and you'll get a magnetic field, because these quantities are sort of regulated. There are safety considerations. So if you admit that, are you saying that you'll get non-zero values or substantial values for these near a high voltage transmission line, but you might not get it beside a transmission tower? Is that what you're maintaining?
Yeah, that's my hypothesis. I think that's correct, that if you were to take this meter, put it up to a high tension line, that would measure high electric field.
And magnetic field.
Well, no, I'm thinking that, well, I'm not quite sure what it would read magnetically. I'm thinking probably, since the field is not going in one direction for any length of time, that it's not going to be able to generate a substantial magnetic field, although I could be wrong about that. But I'm saying that if you took a measurement around the high transmission line and you took a measurement around the high power transmitter, that I would predict around the high power transmitter, you would not see high electrical field like you would around high tension line. You just wouldn't see that. That's my prediction. Because I don't think that what's coming out of the radio antenna is this high power electric and magnetic field. Once again, my hypothesis, but that's kind of a way to try and test that directly. Using something you can actually buy off Amazon.
What kind of an experiment would satisfy you? I mean, when I was in high school, we used to have fun by going outside and taking a fluorescent light bulb, okay, and these long tubes, 6 feet long or whatever, and we wave it around in the yard, okay, holding it in our hand, and it would light up. And the other kids, would go, "How is that possible? That's impossible. There's no wires connecting to it." Well, basically, there would be a transmitter nearby that was transmitting, and that was causing the fluorescent light to light. Will you accept that as proof that there's an electric field in a radio wave?
No, I would just say that somehow power is getting from one place to the other. Does not at all prove to me that it was done by electric or magnetic field. Certainly at the end of the light bulb, I mean fluorescent bulb, certainly there is energy.
So fluorescent light bulb, Franklin.
I mean, all we know there is that energy is being received, and that's obvious. No one would argue that.
There's no wires connected to it. No wires connected to it. None whatsoever.
Yeah, so all that's proving is that energy is being transmitted from one place to the other. The mechanism is still unknown.
Yeah,
I mean, I would not deny that radio transmitters.
I understand your point, except nobody's going to accept it. I mean, we already know what's going on, and you're just swimming against the tide of knowledge.
Exactly. Okay? That's exactly what I'm doing. Just like Copernicus did when he suggested that the Earth is not the center of the universe.
Nowhere. This is getting us nowhere. It's just a waste of my time.
Well, sure it is. I mean, that's like saying Copernicus is wasting his time
No, it's
swimming
not.
against
Well,
the tide.
let's talk about something. Let's talk about something that we can learn something rather than unlearn something that we already know.
But we don't know. That's the point. I'm saying that we don't know how the radio wave gets from the transmitter to the receiver, how that thing creates currents. Or actually, mainstream things say no. Right? You're right that mainstream things say no, but I'm
Franklin,
saying that
we had this discussion last night with David DeHilser, and he said we don't know what light is. Okay, and I'm sorry, I don't think a physicist is going to agree that we don't know what light is.
well, then
any
tell me
physicists here that agree that we
what is
don't know
the
what
shape
light
of a
is?
photon? I mean, what is the shape of a
Do we
photon? I
not know
don't
what light
think.
is? Anybody here agree with the statement that we do not know what light is? Anybody agree with
Yes,
that?
we definitely do not know
Disagree
what
with
light
it?
is.
There you go.
We know
You're
what light
one
does, but we
person.
don't know what it is. That's why I'm
Well, what do you
proposing
mean we
that
don't
light
know what
has
it
this
is?
particular shape. If you ask someone,
Okay,
what does a photon look
what
like,
is
mainstream
it?
will not tell you.
Well, I just think this is pointless to discuss. I mean, we do know. That's not what the issue is. The
Well, then
issue
what is
is
the
the
shape of a
explanation
photon?
that physics books give us. Hold on. The problem is the explanation that the physics textbooks give us. Okay, when you parse it out in detail, causes confusion and ambiguity and uncertainty because they don't have a very good description of what they're talking about. Their theory mathematically doesn't really hold together logically. That's what the problem is. It's not that we don't know what light is, it's that their theory that they attempt to go through all the proofs in a logical sequence doesn't really hold together. And because that doesn't really hold together, people argue about different aspects of the places where it's confusing and ambiguous. Like, for instance, displacement current. Okay, what is displacement current? Well, if you look in the textbooks, and you read that, you go, I don't really think I understand that. Well, that creates a point of confusion. Well, if you think that the description in textbooks regarding what displacement current is doesn't make any sense, and I agree with that, then you could say, we don't know what light is. Yes, I could agree with that. But that's not really saying we don't know what light is. That's just saying we don't understand the physical description given in the textbooks of what it is. That's got flaws in it.
So it's more of a degree. It's like, we've got it like maybe 98% correct, but this other 2% is killing us. Or I could say we got it 100% wrong, and must be a completely alternative explanation for that. But, Harry, that's sort of what the dissident community is here for. We could all be wrong, and maybe we are wrong. And have been wrong for the past 100 years.
Hold on. I don't think the dissident community is here to confuse everything and advocate incorrect theories, because the mainstream has got a confusing logical element of what they're talking about in their textbooks. Okay, so we could point to displacement current as a pretty good example of that. Now, the mainstream response is, oh, no, there's no problem at all. They'll just keep on teaching and claim there's no confusion and no problem. And then the people in the dissident community will keep arguing about whether or not there is displacement current. And then, so it'll never get resolved. Okay. And that's what the problem is. The problem is because the dissident community takes these positions like yours, which is mainstream's completely wrong. They're not going to pay any attention to what you say and never fix the problem that's in the textbooks that's confusing people.
Well, it could be that the reason why they cannot fix that problem is because it's wrong. Now, maybe it's not wrong, but maybe it is, right? Maybe it's as confused as the whole flat Earth theory, right?
Well, there's another aspect of what the textbooks say, and that is they say that the magnetic field and the electric field create each other, and they say that there's an interchange energy of the magnetic field in the EM wave and the electric field in the energy in the EM wave. Well, that doesn't make any sense, and that doesn't correspond to the diagrams that they show when they show you the diagram. So they say one thing and confuse you by saying that the electric energy and the magnetic energy interchange, and then they show you a diagram in which they don't interchange. Okay? Well, okay, are they going to fix this confusion? No. We as dissonants come along and say, oh, your theory is completely wrong because you've got the statement in the textbooks. They're not going to fix that just because you say that their theory is all wrong.
Well, that's true. That's the lament of the dissidents. But someone has to be out there and say what might actually be working, right? That, someone has to say the Earth is not the center of the universe. Someone has to, do that. So.
Well,
now, I could be wrong, but I'm just thinking that it makes more sense.
Ether theory people say, oh, we've got this right theory. They say that the ether allows the electric energy and the magnetic energy to be interchanged because of the way the ether oscillates and acts mechanically. Okay, so that means that the electric field and the magnetic field would be out of phase by 90 degrees or whatever, okay, because the Pearl equations say so. But the experiments with radio antennas don't indicate that at all. They indicate that the fields are in phase, and then the mainstream and the textbooks say all the fields are in phase. Okay, because we have this confusion and this ambiguity about what is the correct statement of the electric fields and the magnetic fields in the EM wave. You've got people who are inventing ether theories, which basically cannot ever be consistent with the experimental facts. So ether people are wasting their time because mainstream has got this confused Maxwell EM theory, okay, which says different things in different places and doesn't really have a complete consistent story. So we're going, oh, let's throw out all of Maxwell's equations. Well, the mainstream people aren't going to agree with them. Okay, oh, we believe in the ether. Well, the mainstream people aren't going to believe in that either. So basically, we as dissidents aren't helping to solve the problem. We're making it worse.
I don't know if that we're necessarily making it worse, but it's true that they don't pay any attention to us. But it doesn't necessarily mean that we're wrong.
You're advocating theories that are totally not based on experimental facts. So as soon as you start doing that, they're putting it out.
Well, the experimental fact.
Anyway, that's a big problem.
Well, the experimental fact is that no one's been able to measure the electric or magnetic field. That's why I keep on challenging people to show me that. If you can show me that, then I'll shut up. But experimentally, no one's shown me that.
That's not really relevant to anything. That's really not a problem. That we already know the answer to. We already know they exist. So wasting a bunch of time arguing about it doesn't accomplish anything.
It does.
As I pointed out before, you can certainly see the effects of magnetic and electric fields on things like splitting spectral lines and these various Zeeman effects and so on. You can measure that and see that. It's an indirect form of measurement, if you like.
Yeah, so I'm just saying there must be ways of doing that, right? Like if you have like some atomic effects that could possibly measure an incoming ambient electric wave. That's just for the experimentalists to do. Just show me some experiment that actually shows that. And I was like, okay, I see the electric field, I see the magnetic field, I see they're at 90 degrees, and I see they're in phase. Those are the four things you got to prove about the electromagnetic wave experimentally, and none of that has ever been done. Right? That to me is a gigantic problem. Right? All we know from the experiments is we put energy in one hand and we get it out the other.
Hold on. You're saying what again? Repeat it again so I can understand.
There are four things that should be. There are four things that should be experimentally provable about the electromagnetic wave, and one is that you should be able to detect separate electric field 2, you should be able to detect the separate magnetic field. 3, you should detect that they are 90 degrees to each other. And 4, you should be able to detect that they are in phase. Those are 4 experimental things that we should be able to detect about the electromagnetic wave according to the electromagnetic equations, right? That's fair.
Okay, so I'm a physicist, and I'm going to tell you that's already been done. Look it up in the books.
No, I've looked it up in the book, and they don't say anything about any
Well,
experiment
it's in
doing
there,
that.
Franklin.
I have looked.
It's in
It's
there.
totally no experiments. They
You're
just
not
show
looking
you
in
the
the right
picture.
place. You're not
So
looking
I've
in the
done
right
it.
place.
I've done the research. You can't shut me down that way. It's not in the book.
Hold on. You're completely confused when you say separate magnetic field, separate electric field. You can't separate them in. Okay? So,
Of course, you can separate them. Those are
this is
two different measurable fields.
Hold on, Franklin. You're setting up requirements, okay? And the way you set up the requirements to do the proof, you're essentially preventing it from being proved by what you're demanding to be proved. So you're asking to prove what can't really be proved.
Sure, it can be. There's no reason why you cannot measure a separate electric, separate magnetic field. So are two physical phenomena that can exist in space simultaneously. Why would that be impossible to prove?
It's been explained to you over and over and over again, and you don't understand it. And something.
No, you've never explained it. Barry, you have never explained it. You can't use that argument.
Well, Franklin, you're just wasting our time.
No, I think we're not. This is the most important thing, is I am questioning the experimental basis behind the electromagnetic wave. I mean, you're saying that they can't be done, but as far as I know, yes, it can totally be done, and you have not explained to me why it cannot be done. You just keep on saying, oh, it's been explained to you over and over again. No, you've never explained it.
Separate from the magnetic field, Franklin. You can't do it. They're both the same. They both are power. So if you detect power, the electric field and the magnetic field, they're both at the same time. They're not separate.
Yes, they are. If I have a magnet and if I have a Van de Graaff generator, I can take that field meter and I can measure the electric field. I can measure the magnetic field simultaneously. There's no problem. They're definitely two separate measurable quantities. I mean, any physicist would probably tell you that, right?
But you've also said that if you put these meters beside a transmitting tower, a radio transmitting tower, you believe that you'd probably get negligible values. So, using your own argument, do you therefore think that the transmitting tower is not transmitting a radio signal?
No, it's transmitting a radio signal, but what it's transmitting is just a pressure wave through a physical medium, having nothing to do with electric fields or magnetic fields. It's like a gigantic speaker, transmitting at 20,000 watts. But instead of sound waves, you're getting a wave in whatever is the medium of the electromagnetic wave. And that's all it's doing. That's my hypothesis, that the radio transmitter is just vibrating whatever the medium of the radio wave is, right? And that's all.
Either is an electromagnetic disturbance or it's not. I'm not quite sure of your position. Is it an electromagnetic disturbance? You say it's a disturbance in the medium. Well, I agree with that, but I say, well, that is an electromagnetic disturbance.
No, I'm saying that it's just like a sound wave. I mean, I want you to understand this. I'm saying that
it's like a sound wave as well, but it isn't a sound wave.
Yes, it is a sound wave. That's the thing that I have to. I mean, that's the big block, because I'm telling you that the electromagnetic wave doesn't have anything to do with electro or magnetic. It's one of the most misnamed things ever, right? It's just a pressure wave, just like a sound wave. That you understand that. That's my hypothesis.
But sound needs a ponderable medium, the sort of medium that we we know and we measure and we weigh, like a gas. And these disturbances don't need that.
That's right. No, actually they do. If there is a medium, like I've said, you know what my medium is. My medium is just like neutron field, positron electron dipole field.
Well, for me, it's the ether.
Yes, there's definitely an ether,
but therefore it isn't identical to a sound wave. It's analogous. We agree on that.
It is generally physically identical to a sound wave. That's the main concept you have to get. That physically, it traveled exactly the same way as a sound wave. The only difference is the medium versus air versus positron electron C. That's the only difference.
You think it's a compression wave, a longitudinal compression wave. And I mean, my position is that is probably doubtful. It's probably a different type of disturbance. But I do concede that there is a great analogy. But I would be hesitant to say that therefore it is identical.
Well, why do you have that hesitancy, I guess, is my question. Well, certainly it totally works for sound waves. We know how that works. So why couldn't that work for radio waves? I think that's perfectly analogous. So,
well, it might be nice to think that it could, but
it's not nice. It's how it actually works. That's how I'm saying you.
But why? I mean, through the Maxwell's equations and the electromagnetic theory, which you can throw out and you can doubt, but we have a model which fits many experimental phenomena. That indicates, contrary to what you might believe, but nevertheless, it indicates, to my mind, that you have a transverse wave operating with the E and H fields in phase and at right angles and all that sort of thing. And that seems to work. And it seems to be at variance with what we know for sound waves, where you have a compression and rarefaction occurring in the medium, which is a ponderable medium. The ether has different properties. It has magnetic and electric properties. So, I say there is a similarity, but to say it equals that, as I say, I use the word nice. It would be nice to believe it. It would simplify things, but I don't think it fits in with our existing volume of theory.
Well, I'm just curious, where do you think it fails? Where do you think the sound model hypothesis fails?
Well, for one thing, it works through what we conceive of as a vacuum. Now, I know we have our own, descriptions as to what is in the vacuum, but I mean, it's not a ponderable medium. So, in other words, if you evacuate a flask and you put a bell in it, well, you won't get the vibrations. But if you evacuate a flask and put a laser in it, you'll get the output. So that's one fundamental difference. The medium.
Well, I mean that's a question of whether there is a material ether in the jar, in the vacuum jar. I mean, but if you presume that there is, and the evidence you could point to is that you can pop positrons and electrons out of that same vacuum, so that indicates that vacuum must be filled with positrons and electrons. I mean, there's also the mainstream concept of virtual particles, which you're saying that positrons and electrons pop in and out of vacuum space all the time. I think that also indicates that the vacuum is filled with something, probably positrons and electrons. We also have the Lamb shift experiment, which definitely says that the only way they can account for the spectral lines, the way they see them, is if space is filled with positrons and electrons. That's even a conclusion that mainstream comes up with. So, I mean, but presuming that there is a sea there that we just can't see because it's neutral, then what's the problem, right? Because I'm just saying that the medium might not be that. I mean, the medium could be anything, but presuming that there certainly is a medium that's there. I mean, that's not an unreasonable thing to presume. I mean, everyone thought that prior to like 100 years in Einstein, right? Everyone thought that there was this ether. The
No,
lumiferous
I believe that myself. There's no argument there. It's just when you ascribe an identity between the way these positrons and electrons or whatever you want to postulate behave, and an actual baffle, which is hitting against a medium and getting these ponderable particles, these molecules, which are vibrating and taking up the energy in a microphone and giving back the energy in a loudspeaker. When you say that is identical, with respect, I think you're contradicting yourself, because you're already conceding that there is a fundamentally different model, which I subscribe to. I agree with this. Whether you call it positrons or electrons, I just call it an ether with electromagnetic properties. So it is analogous to the sound, and it works very similarly. That's true, but it isn't sound. I mean, it's disingenuous with respect to say it is. There are differences, which you've just described yourself.
No, I mean, in order to understand my viewpoint, when you guys say that a radio transmitter is this electromagnetic wave phenomenon, to me, that's like if you were to tell that when I'm talking, that is also an electromagnetic phenomenon, and that what's happening is that I'm creating electric and magnetic fields, and that's what that is what's going across the space here and hitting my microphone. You see, to me, if I were to suggest that, then you could see how ridiculous that would sound, right? That for me to suggest that the sound wave is this, it turns into this electric field and magnetic field, which are crossing at 90 degrees. And then that hits my microphone, and then that is being decoded into an electrical signal. I mean, obviously, since there's an electrical signal at my microphone, then I must have been transmitted electrically, right? That would be the argument everyone is giving me, right? Because the microphone is outputting electricity, so therefore the phenomenon from my mouth to the microphone must be electric, right? It's obvious, right? But it's obviously wrong. So that's why, I mean, it's important that you understand the hypothesis here, that radio wave travel exactly mechanically the same way as sound waves. And that's just because of my physical bias, right? Because I'm a physicalist, right? I like to explain everything in terms of, say, billiard balls and Newtonian mechanics, right? I don't like all this mysterious field stuff. It just doesn't work for me. What does work for me are direct physical analogs. So, but I do want you to understand, which you don't seem to be getting, which is that, I believe the radio wave transmits exactly in the same physical manner as sound wave. It's received at our antennas in the same physical way as a microphone receives a sound pressure wave. It literally pushes against the diaphragm of the electrons, and that's how I think that works. So, but I'm just going to explain why is it you refuse to accept that. I mean, clearly you refuse to accept that it literally transmits in that way, and that we have things like Maxwell's equations, which do apply to real charges and do apply to real magnets, and all of that stuff is absolutely true. But what you can't do is take away the magnets and the charges and have those fields exist in the middle of space somewhere. You just can't have that, right? That's one of the main conflicts, and that's why they need, like displacement current, so they can have a pretend current, a pretend charge out there to make these fields actually exist in the middle of nowhere. But what can exist out in the middle of nowhere is a compression wave, right? If there's a medium out there, all you need is a compression wave. We know that can exist without any charges being present, without being any magnetic fields or electric fields being present. And we know they will travel long distances, right? It's not like you create an electric wave or a magnetic field over here. Somehow it manages to walk its way across billions of light years to reach us on Earth and then reconstruct itself. I mean, that is the crazy thing, which is what we're expected to believe. Much easier to believe that just some electron over in some distant sun caused a pressure wave. That pressure wave has been traveling to us all the way billions of light years to hit us here in Earth in the shape of a rod. That's what I'm trying to say, that it's a wave packet, right? But it's just like sound. But there are some differences because sound is in a lossy, friction-filled environment, but apparently the medium, whatever it is some kind of frictionless superfluid, so that once you institute a wave in it, there's no friction, it can travel forever. And it doesn't disperse. I mean, that's definitely something that doesn't happen with sound waves. I mean, you could never get a sound wave in the shape of a rod and have it hold, right? Just due to the frictional force, it's not going to hold. So we can't see a lot of things like the transverse polarization effects in sound, or you can, but it's very hard to see. But otherwise, that's why I keep on advocating, and that's just like my opinion, that the radio waves are just like sound waves, just propagated in different medium, and that's the only difference.
Well, I might even go further than you in some respects. I mean, I concede that, or I believe that electromagnetic waves do attenuate in distance. You've just said that you think it doesn't. So I think that's more analogous to a sound wave.
Yeah, and that sound waves definitely attenuate. That you can't get a sound wave to travel forever, although probably, I mean, that's not something that we generally see, but we do see. Certainly, one of the characteristics of light waves is that they can travel forever, pretty much, except for maybe they get redshifted or something, so they can't quite travel forever. But generally speaking, let's see, we've got some comments here from Alistair. Let's see here. Well, Alistair, you can't come off of mute if you would like to make your comments, because you're saying things about radio waves are polarized, sound
Sure.
waves are not polarized.
I'll comment. I didn't experience much opportunity to comment prior. Sorry about last week with my signs. My computer had a sound problem, and then it forced me to do some update that took like 20 minutes, and I was like frustrated by it. But anyway, so sorry about that. So yeah, see, sound is not polarized. The EM waves are polarized, and sound, it exists or it doesn't exist. But EM waves are anomalies in. So they go negative, positive, negative, positive. Sound doesn't go negative, positive. Sound goes only positive. There's no negative sound.
I'm not quite sure what you mean by that, because certainly all sound is a push and a pull. Certainly, we measure that on our microphones.
It's a push and a release of push. It's not a push and a pull.
Well, how could it not
pull in air?
Because if it didn't pull, it was purely a push, then it could never keep on pushing again.
There's no such thing as pull in air.
Well, what's going on in a microphone diaphragm then?
Franklin, you can only suck water 30 feet up a tube because there's no pull in air. There's only push, period.
Well, you're talking about pressure? We're talking about sound waves.
Sound waves are pressure. You can only have pressure or lack of pressure. You don't have suction. There's no such thing.
Yeah, but that's what we're talking about. We're talking about a wave. It's a push and a pull.
You just said pull. What do you think pull is? There's no pull.
Yes, there is a pull. That's what happens in a microphone diaphragm. It pushes in and pulls out. Same thing happens at a speaker. It pushes out and it pulls in.
There's only push and release and opportunity for push to have an effect. There's no pull.
Well, what is going on with your speaker then on your radio? It's pushing and it's pulling.
Are we talking about air or are we talking about diaphragms?
We're talking about the effect of air using diaphragms. This is how we generate air. This is how we generate sound.
The passage of sound waves through air versus the passage of light waves through whatever medium, the electromagnetic field. So where did diaphragms suddenly get introduced and why?
Because it's just a generator of waves. If you have
Okay.
a wave, there's definitely a positive, and then there's definitely a negative. If you're talking about an oscillating
Okay,
signal,
so can you negatively move your diaphragm? No, you can only move it or not move it.
yes, you can negatively move your diaphragm in the direction that diaphragm can move. Definitely, you can change
That's
the magnetic
motion
field to
in
move
that
it in
direction.
and move it out. That's how speakers work. Definitely a negative direction.
Yeah, you realize that speakers are not a wave generator in the way, like, you realize they have shape, right? They're a cone,
Yes,
so they generate a shaped wave.
yes, they do.
Okay.
Also, radio
All right,
antennas generate a shaped wave.
I'm gonna let you carry on, Franklin, because I'm not seeing the same eye as you are, and you just go right on ahead.
Well, I mean, that's the point of the science chat, is to figure out what the differences are.
Right.
And I mean, that's the whole point of this chat, right?
All right. So I'm telling you that a pressure wave in air is not polarized, but an EM wave is polarized. Do you disagree or agree with that?
Well, there are experiments. I just sent a reference around an email about a guy who said that he could detect polarized, even circular polarization in the experiments that he did. Now, when I did have a chance to look at that paper, and it has to do with if you have waveguides to control the wavefront, that yes, you can even polarize sound. So that is not necessarily a showstopper.
All right. If you want to stand on them being one and the same, I am just going to give up.
I mean, that's just my hypothesis. I mean, that's what we're
All
here
right.
to discuss. I mean, is that a correct
I
hypothesis? Or is that the wrong hypothesis?
I think that Harry Ricker went to EM wave school. I happened to go to pressure wave school. And so I understand pressure waves. And Harry understands EM waves. Maybe I don't understand EM waves well enough, or maybe Harry doesn't understand sound waves well enough to convince you, who thinks you know both better than either of us know what we're talking about. That's fine. You just carry on, because I give up. Sound waves aren't polarized. You can put polarization in it because you can use shaped impellers of sound. You could put a fan, and that's going to create torque in the air. But that's not the same as it's just, that's not sound. That's a torqued pressure wave is not sound. That's two different things. Sound is non-polarized.
But even that doesn't tell you whether it's electromagnetic wave. I mean, you could admit that, yeah, there's polarization, but still, that's no direct evidence that it's an electric or magnetic field. All that says is that there's something in the signal that can detect a vector angle. That's why I suggest that the polarization happens because the shape of the photon is a rod, and the rod is quite capable of encoding that polarization. That's how I solve that. I mean, if you think polarization is a problem, all I have to do is show that a compression wave can encode polarization, which I have done.
We're not talking about you bait and switch. You talk about sound, but then all of a sudden you talk about a detectable wave. Detectable by what? By your ear? That makes it sound? By a sound detecting device can detect the torque in the air?
I mean, that would be an interesting experiment, because I'm thinking that actually, yes. I'm thinking that with a sufficiently sensitive amplifier, if I just sent a sound wave against a metal antenna, we should actually be able to receive that.
And yet, the formula for turbulence is one of the Millennium Prize challenges that stands unsolved, but here we are hearing that you're confident.
Well, what is this Millennium Prize that you're talking about?
What did I don't know, Tesla or Einstein, one of those guys said something like, if I died and could ask 2 questions, I'd want to ask about I don't know, the afterlife and turbulence, because I'm sure I'd get an answer to one, I wouldn't get an answer to turbulence or something like that. Because there's, I don't know, you'd have to look it up. Look up how well does humanity understand turbulence or something like that. So I don't know. I'm just a little frustrated by that we talk too much in circles, and I'm doing it right now too. So I just want to shut up like I tried to 10 minutes ago. You continue. I'm giving up.
Well, I wish you wouldn't give up. I mean, that's what we're here to discuss. I mean, as dissidents, this is what we do. It's like mainstream, they think that, X, Y, Z. Dissidents think it's A, B, C, right?
Yeah, go ahead. Dissident away.
I'm not really sure that's true, Franklin.
Well, if it weren't, then we wouldn't be, dissidents, right? We'd be agreeing with the mainstream, and then,
Hey, dissident doesn't get to make up unicorns and then claim unicorns.
Let's talk about Einstein's theory of relativity. That would be a good example of dissidents versus the mainstream. What would you say? Why would you say Einstein's wrong? Tell me why Einstein's wrong as a dissident.
Well, I'm saying, you know my position, Harry. I'm saying that Einstein is actually right, and what's wrong is the dissident's interpretation of Einstein. That's my stance.
I would question
there
the
you go.
claim that the center of black holes are infinitely dense.
So both of you are talking there, so one at a time.
All right. Yeah, I'm mute.
Well, my point is basically is you're going to get all kinds of different opinions. Okay. How do you solve the problem? What is the problem that needs to be solved? Then tell us how to solve it. What is the problem with Einstein's theory? What's the problem?
Like I said, no problem. As written is absolutely correct.
Okay, so why are dissidents objecting to it?
Because they're misinterpreting him completely. I mean, he's twisting his words around to be the exact opposite of what he meant.
Why don't we speak on our behalf instead of speaking for all dissidents?
I'm sorry I brought it up. Sorry.
But once again, my opinion on Einstein is rather unusual. I think he's absolutely correct. If someone were to read Einstein's paper,
why don't you let some other people give their opinions?
That's totally what I'm doing. I'm totally letting people give their opinion. I mean, letting you give your opinion.
Well, you complained about dissidents misinterpreting Einstein, Franklin, but surely it's the mainstream. I mean, there's an accepted theory of special relativity or general relativity, which the mainstream put out. And any ostensible misinterpretations are due to the mainstream, because those are the theories. Now, you're saying that's not the real correct theory. There's a really correct theory, which is pure. And if you go back to the original publications, you'll find the theory is at variance with the mainstream interpretation, which is accepted by dissidents. In other words, the dissidents are using the mainstream interpretation as the theory and attacking that.
Yes, that's exactly what's happening. That's totally correct. The mainstream has misinterpreted it. The dissidents are then using that as a straw man, and it's obviously wrong. So.
Okay, it's obviously wrong. So that you could have answered Harry that way, but I don't know why there's some idealized system whereby this man 100 years ago said things which were perfectly right, and he's been misinterpreted, and that misinterpretation has led to most people saying that the misinterpretation is correct, and a minority of dissident people saying it's incorrect. I mean, it's almost like idealizing a religion like saying Christianity never existed because it's been misinterpreted and misapplied. I say, by their fruit shall you know them. So we take the theory of relativity. Now, if I go to the original papers, I find that the evidence for what you say fairly weak. I mean, I think there are some minor misinterpretations, but I think in general, it is true. I mean, Einstein said that the speed of light is independent of the motion of the source.
No, he didn't.
He did say that. That's a second.
No, that's the biggest lie ever.
No, you've listened to what I'm going to say.
Read the paper. There's nowhere in this paper that said that the speed of light is constant in all reference frames. That's not the statement.
The actual words he says, I could put them up on the screen now, is he says the speed of light is independent of the speed of the source of the light. That's exactly
what he says. That's true.
That's what he says, yes. And that is correct.
True.
You didn't listen to me. You thought I said the opposite. Now, that is what he says, yes. However, and that is correct. That's classical physics, actually. Same with sound. However, if you apply the transformations which he uses, the Lorentz transformations, and his principle of relativity, that there's no difference between a stationary source and a moving object, or if you take the object to be stationary and the source to be moving. If you take that, well, then it's totally reciprocal. And he does actually develop then a system whereby the speed of light is independent of the speed of the observer. Now, he doesn't say it in black and white like that, but he actually does effectively use that principle. Now, that is incorrect.
You kind of lost me there because you kind of said contradictory things.
Well, he possibly said contradictory things, yes. But
I mean, I'm saying that you were saying contradictory things. I mean, to be clear, what Einstein set up was a stationary frame. He used the word stationary like 51 times in his 1905 paper. He uses the word stationary 51 times. Refers to all actions occurring relative to that stationary frame, right? Now, that's a special frame, which is what mainstream is the thing that they throw out. This is the biggest misinterpretation, that you can get this symmetry. There is no symmetry. Everything is done relative to the stationary frames. If you send out two twins, you have to make all calculations relative to that stationary inertial frame. And if you do that, you'll find out that the twins don't age in some weird way where one has to be older than the other one has to be older than the other, because you think the speed is relative. Now, you measure the speed relative to a frame, that determines the absolute speed for the twins, and then you can apply the relativistic time dilation equations, and there's no contradiction. And that's what Einstein really said.
No, he didn't. Einstein is quite clear. He's talking about the twin paradox. And he actually says that the one who moves away and accelerates back actually does age less than the one who remains on the Earth. He does say that.
Yes, that's true. Once again, what Einstein says is true. But what is false is if you send two twins out and then they both have to be older than each other. That's a paradox. And that's wrong because they try and make it so that the speed of light is constant in all reference frames, which is the completely wrong opposite idea of Einstein. That was never in his papers.
No, but he does say that when an object, for example, shortens in length because it's moving relative to a stationary observer, he does say that's totally reciprocal. He says from the point of view of the moving rod, the rod which has remained stationary, in inverted commas, is shorter. He does say that.
Well, see, now you're switching topics, because the length time dilation and length things are definitely two different kind of effects. So I don't know why you decided to switch.
Well, they're obverse. I mean, he takes the length of an object to be decreasing. Fitzgerald Lorentz contraction. When it just was in motion, and then he takes the time to be dilating in the same way. So it's just one is the reciprocal of the other, and this is the way you get a constant speed of light. it's all based on a modification of the Lorentz transformations to be made totally reciprocal. I think
No,
that's
not, whenever you say the word reciprocal, that is the massive mainstream misinterpretation. There is nothing reciprocal about what Einstein actually said. There's nothing there. Everything is measured relative to stationary frame. Therefore, everything has absolute velocity, and therefore there is nothing that can be reciprocal. That's where we have all these problems. All concepts having to do with reciprocal are in fact wrong. That's where we get all the paradoxes from. And it's not anything that Einstein said.
So why should these words of this great man be so traduced and misinterpreted so that we have a theory which is incorrect, but it's quite at variance with what he said?
No, the theory as written, and if you do experiments on, is totally correct. Right? We do all these experiments.
Why? How come that such a corruption has existed? That I disagree with you, and I can give reasons if we have time. But if we have a theory which is correct, that's been totally twisted around and reduced, so that you have from that an ostensible theory which is actually incorrect, but is not due to the author of the original theory. What's the reason for that? Is it political?
Yeah, good question. Why did it? I mean, what you just described is what is my hypothesis on what's going on with Einstein, right? It's like Einstein, he wrote a perfectly reasonable, correct theory, and then the mainstream got a hold of it, and then started twisting it all up. And then, the dissidents point out, hey, mainstream, you twisted that all up. But they don't recognize that that was an incorrect interpretation in the first place. Now, why does that happen? I don't know. I mean, you'd think there'd be more sensible people
Franklin.
to
Franklin,
make that
if what they were saying was wrong, why didn't Einstein correct them? He had many, many years to correct the theory that the mainstream was putting in the textbooks. He had Henry Bergson, who at one point published a book, and Einstein could have said, when Henry Bergson published the book that he published, okay, which would tend to agree with the theory that you're saying, that Einstein agreed with the people. He didn't say to the physicist who completely destroyed Henry Bergson and his reputation, he didn't say, oh, hey guys, what I meant was what Henry Bergson is saying and not what you guys are saying. No, he didn't do that. So I don't think that's really a supportable position on your part. But the real issue here, as far as I can say, excuse me, let me finish. The real issue, as far as I see, is that dissidents can't accomplish anything because dissidents don't agree with each other and don't have a point of view that is consistent and pointing out to mainstream what it is that they need to fix. And so mainstream is never going to fix it because there really isn't any consistent reason for them to change anything in their theories. There's only just a lot of different opinions saying that they're wrong, which they just dismiss. So as long as there's no consistency of opinion amongst dissidents, I don't see why mainstream would even consider changing it.
Well, Harry, absolutely, everything you just said there is absolutely correct, and that's why groups like CNPS exist, so that at least we can talk to ourselves. Because obviously mainstream's not going to pay attention to it, but we still have this outlet so that, if we want to complain, we want to say mainstream is wrong. It's like, we can go continue to talk about that on Saturdays for 2 hours just to get out our frustration.
Standard answer to any criticism is you misinterpreting the theory. Okay, so if you criticize something that's, say, you in the theory, or as Mr. Josephson said to me, he said, I'm clueless. He said I was clueless, which I thought he was the clueless one. But
that's interesting, Harry. Well, yeah, you brought up that there was somebody, Harry, whatever, what was his name? who wrote the book, who got criticized because he
Brian
was,
Josephson, Nobel Prize winner. You probably heard of him.
who was it? Let me write his name down. I got to research him. What's his name?
Brian Josephson, something to do with the Josephson effect. Okay, he said I was clueless because he couldn't refute my argument where I was saying, basically that mainstream had made a mistake and where the textbooks were in particular displayed are. And he said I was clueless. That was his rebuttal to my argument.
Now, to your, because I'm kind of wondering this as well. While Einstein is alive and everyone was like screwing up his theory, how come he didn't say anything? Now, I thought I heard some quote from Einstein to the effect that you have taken my theory to the point where even I don't understand it. So it could have been that even he was overwhelmed by what the mainstream was doing, and he couldn't figure out whether what they were doing was wrong.
Excuse me, I think that's in reference to Minkowski and his mathematization, and Poincare also had a mathematization of it, and where they were using four-dimensional space-time vectors and vector calculus and that sort of thing.
Yeah, so I
don't
totally
think that he was saying that I fundamentally misunderstood what he was saying. I think he was saying that it had become so complicated mathematically, it's difficult for him to understand what they were saying.
Well, it's not in his original paper, admittedly. In fact, not even a mention of it. But the Michelson-Morley results, later on, he does concede that, according to his way of thinking, they should come out to be zero, because that's what the theory of relativity, special relativity, predicts. And he got very exercised with regard to the Miller results, which seemed to indicate a positive result. And he started dismissing all those. And, Miller said he wasn't given a fair hearing by Einstein, because he admitted that if the Miller results were real, then it destroyed his whole special theory of relativity. So I don't know how you feel about that, Frank, whether he's interpreted there as well.
Yes, I do recall that. I mean, that is an interesting factoid, that he thought that if you could measure the ether wind, basically, that would completely destroy his relativity theory. But you're right in that I would think, well, no, it really shouldn't have, because I claim that his theories were basically an ether theory. I mean, basically, it was a Lorentzian ether theory that basically relativity was based on. So I don't see why he should have had any problem with detecting an ether wind. Yeah, that's curious. I don't know why he would say that.
And by the way, I mean, if what you've just said is your view, that it's basically just a Lorentzian ether theory, well, then I submit that one might dismiss it and say he did nothing, rather than say he did something which is misinterpreted, because he just rewrote Lorentzian theory, ether theory, and maybe made it disguise it so that it was a new theory. But I think you'd have to dismiss it and say he did nothing, not he did something that was misinterpreted.
Well, I would agree with that statement. I would say that everything that Einstein came up with, even E equals mc squared, existed well before he put it to paper. And you notice in his paper, what's unusual to scholarly standards, as he has no references, none, right? He just, typically that's what you do. You always cite your references. Einstein cites none, which would generally get your paper rejected in any current peer-reviewed journal nowadays, right? But somehow that was okay for Einstein to not reference anybody. But clearly, all this stuff, it existed in Lorentzian ether theory, before, right? And I don't know why is it he went like quote unquote viral, right? I still don't understand why some stupid video for some reason gets like 3.5 million hits, and my video that I worked 3 months on gets like 5. Why is that? I don't know. But yeah, what you say, I would agree with, and I don't think Einstein really came up with anything that was novel. It was something like, he came up with this paper, Max Planck liked it, so he made it popular, and then they did that experiment with the solar eclipse, and, somehow we entered this whole Alice in Wonderland, up is down, left is right, black is white, world of physics. Right.
Well, those are a couple of other examples. I mean, I would maintain that his view with regard to the deflection of light in that solar eclipse was incorrect. And I would also maintain that his view that the calculation of the deficit between the observed and theoretically predicted precession of the perihelion of the orbit of Mercury, and that you needed the general relativity to get this formula. I believe that was incorrect as well.
Well, yeah, definitely the solar eclipse.
We lost.
Definitely solar eclipse.
I just want to put out there my comment, which is, why would anybody who is writing textbooks and teaching students physics and working in the government, at the National Science Foundation or any of those places, why would anybody consider changing the textbooks to get the physics right just because we tell them that they need to do that?
Well, certainly they shouldn't do that just because we tell them to do that. They would only do that only if they would get some careful investigation and experiment and prove that what was in the textbooks was wrong. And then that would be adequate reason to change that.
Well, their answer is basically, if you point out a difficulty or a problem, like for instance displacement current, their answer is you're close. So how do we change that? How do we go from being?
I mean, it might seem a bit extreme. Maybe a bit extreme, or maybe smacking of witch hunting. But just as in the political arena, we have corruption, and it's very hard, well nigh impossible, to get the politicians to address any of these perceived practices, by going to them. They'll always be defensive. So what we have in society, we have the possibility of having these sort of forums, with these investigations, which are set up maybe under the aegis of Parliament or something like that, or Congress, whatever, and they investigate and they frequently find that these politicians have been behaving badly. Now, so here's the principle, which seems a bit far-fetched, but if we could get some sort of forum which could investigate the way physical scientists have behaved and the way they have not accepted evidence from outside, and to show that perhaps they're corrupt in a way, that they've been protecting our whole infrastructure and what they've taught all their careers and not allowing any open investigation, notwithstanding the fact that science claims to do this. Well, then, we could attack them this way, and we could maybe get somewhere. But it smacks, as I say, of witch hunting. But it seems to be the only way of doing it, to have a sort of an official type of investigation under some authority, maybe some international authority, rather than just a few crackpots like us who are appearing every Saturday afternoon, talking and writing the odd article here and there.
Well,
I'd like to comment on this. Let me comment if I could. My understanding is that Ivor Cat is trying to do something similar to what you just said, and he's apparently tried to approach journalists, but apparently journalists aren't really an issue, which I'm not really surprised, because I think journalists believe that what scientists say, because they're a source of authority, and journalists like to, say scientists say such and such, and use that as an argument for political position. So there is, Ivor Cat is one of the few people I know who's actually attempting to do something in this political arena as you described.
He doesn't seem to be getting very far, though, Harry, perhaps. Unfortunately.
Yeah,
Hey,
that's
this is
because
you
he's
guys-
dismissed as being clueless.
Do you guys
He's
Go ahead,
dismissed
David.
as
hear
being
me at all?
clueless.
Yes. Well, I mean, obviously, I've been, like many people for many decades, looking at this. And the first thing I did when I met a dissident scientist back in the early 1990s, Dr. Karazani, showed Einstein's special relativity wrong. I went to the library and I read about scientific revolution. I read about every time something big came up in science. And what I found was the same repeating idea. And this idea that we can approach the mainstream, we can approach the press and change their mind has never happened in 2,000 or more years of scientific change. It's not happened. In fact, if you read enough books, which I did, on even Newton himself, we have this idea that Newton was totally accepted and he was just, sitting at Cambridge, being worshipped by everyone who knew he was a scientific god. The last sentence of a book that I'll never forget, sitting in the library at Long Beach, California in the early 90s, it said, and Newton spent the rest of his life working at the Mint and defending his ideas to his peers. Now, this is Newton. And so the only way scientific revolution changes, and this has been quoted by many people, I think Dirac said it first maybe, is that a generation has to die. That's the only way it's going to happen. The people who are journalists who make their money off of this, that's what they do. You can watch it on YouTube. You can take Sabine Hassenfelder. She left in 2017. She wrote her PhD at the Large Hadron Collider, and she left. And she wrote the following book. This is the title of it, Lost in Math. Now, she had a great opportunity to try to use her position to change people, to say, hey, we're lost in math. So what did she do? She started her YouTube channel. Now what is she doing? She is worrying about how many viewers she has. So she is no longer doing what I do, which is to really confront science. And that's the reason I only have like 3,000 subscribers. She's got tens of thousands, 100,000 subscribers. Her views go up. What did she do? She abandoned truth that she was trying to talk about in her book to make a living. And so this idea that we're going to change it, or we're going to be the first generation ever in 2,000 years to change mainstream's ideas, we're not. And what happens is really simple. A new model is going to come along. It's maybe from our group, somebody else, that somebody's going to say, this is way better. People are going to start using it regardless. Mainstream's going to call it a bunch of garbage. But if more and more people pick it up, they actually use it, and it becomes useful, it eventually will just take its place, and the generation will die out. I've always told people, and this is what Alexander Unsker, another person who's out there trying to let people know we need to be critical thinkers like this group, that's why he supports this group, comes by, is that we need to try, as Buckminster Fuller says, you're not going to change the world with something. You have to come, by saying if something's wrong, you have to come up with a better model, a newer model that everybody's going to see it's obvious and use it. So we can talk about how to get, and this is one of the things dissidents do. I'll use the terminology in my new model. Oh, they're going to see I use neutrinos, so they're going to come to my model. Oh, I'm using, I say relativity is right. They're going to come to my model. They won't. It's just not going to happen. And I think for us to ignore 2,000 years of people trying to change science, and there has never been a case where mainstream science has changed. It just hasn't happened.
It has happened.
No, it happens. The mainstream gets replaced by people. The mainstream, we get a new mainstream.
How do you explain Einstein himself?
No.
Dissident.
Einstein had so many detractors during his lifetime.
Yes, he did, but he managed to somehow completely.
Because a newer generation like Eddington and other people grabbed upon it. That's why. So it wasn't that he went and changed people's ideas. It took Eddington to do it and then other people to follow it. And supposedly they thought it was a better model because they were all enthusiastic about the idea of light bending gravity. That's where it came in 1919. So, but that's not going to happen. We're not going to go up to somebody and hand them our models and say these are better models. What we need to do, as Alexander Unziker says, we all just got to work like hell on what we're trying to do. And if what we're working on is worthwhile and it's really good, and you put out your book, you put out your paper, and people will grab a hold of it, they will. I don't have this. I don't think this idea that they just haven't seen it. Well, you're giving me an example. One of the things, Franklin, you use words all the time. I did this whole broadcast last night for 2 hours. You throw out words and opinions, and you can just say, well, that's my opinion. You have to back it up. I'm sitting here saying, I read the history of scientific changes for over 2,000 years. I spent months in the library at the time before the internet, and I couldn't find an example of it. Just to say, oh, it happens, anybody can say those words. Words are magic. I can say turtles fly. But you have to look at things. You have to come to the argument with things you've read. You have to come to the argument with more than just, I think it's this way. And so what I'm saying to people is let's keep working on what we do. The more we worry about what the mainstream is going to do or think that they're going to change, might shoot yourself in the head. It's not going to happen.
I think David is right.
And the other thing too, you were talking about relativity. It's one of the reasons I jumped in. Let's look at relativity. First of all, this is the honest God truth. This is a person, myself, who spent 8 years on a movie called Einstein Wrong. Not because I believed it was wrong or not. I gave the chance for everybody. I gave my mom a list of 50 universities to call up. 50. And you know what we found? No one specializes. No one said on the other side of the phone that they were making a living off of relativity. If relativity is such an amazing theory, today I can only name one person on planet Earth that makes more or less a living off of relativity. His name, Kip Thorne. He's from Caltech. When I went to the advanced class to film at a Poly High School, the best high school in Long Beach, where people were going to prestigious physics universities, they skipped all 46 pages of relativity. I asked the professor why. He says, no one relates to it. If relativity is so right, why is it that astronomy clubs have abandoned it? Why is it that most of the people who love science have abandoned it? Why aren't people writing PhDs anymore in it? Why do the particle physicists, the experimental physicists at Stanford Linear Accelerator come onto my film and say they have to unteach relativity to their grad students? What are we talking about? Relativity is good. It's been abandoned by most of the people. You cannot go to a university that says we have a department of relativity. I want to be part of it and write my PhD. It doesn't exist. It's not used in GPS. It doesn't work. We know that. So you have Bill Nye, the science guy. I saw him in person. I met him in person. He stood up with his phone and says, GPS in your phone wouldn't work if it wasn't for special relativity. And I bit my tongue because I was there, because my company paid for it, and I'm not going to make an ass of myself, but I bit my tongue. He's lying to the public because he doesn't investigate anything. He repeats what other people say. So when we talk about relativity, first you got to find me people who even write their doctorate in it. You got to find me a person in a university who even says they're a relative. You know what they all said? Well, so-and-so sort of does that. So we're talking about a theory that no one uses. It doesn't work in GPS. Mass increase is not observed. It's untaught by experimentalists at particle accelerators. Go read the paper or the article we have on Science Woke that Cynthia Whitney, our chief scientist, got her PhD in special relativity. The first thing she applied to it, it failed. Now we're talking about, oh, relativity is okay to me. Well, it may be okay to you, Franklin, but the rest of the world has abandoned it with vigor. And lots of people, even in mainstream.
There are not a lot of really practical applications. I'm still waiting.
There are none. Wait. There are none. Now you can say there are none, because one of the things is, if you say, oh, they use it to find planets, we know by Dr. Edward Dowdy that the curvature of light is going through mass in space, which is called the corona. And yes, we can use that, but to say that's space-time and that's practical, no. Go remember, unfortunately, Ron Hatch, who just recently passed away. He knows they don't use it in GPS. In fact, a 0.56 picosecond difference is because when you add the speed of light to the speed of the satellite, guess what? All the calculations work out. Do you think anybody wants to do that? No, because it's in violation of Einstein's special relativity. So making statements that, oh, it's practical in some cases, it's not. There's no one using it.
Okay, well, thanks, David, for that. But looks like we've come to the end of our 2 hours, so it seems to go rather quickly. So just to kind of summarize, so today we were continuing our discussion of the nature of the photon. So we're asking the question, what does a photon look like? So once again, I gave my hypothesis. My hypothesis is that it's in the shape of a rod. And, we discussed, why is it looks like a particle? Why does it look like a wave? And discussing the hypothesis as to whether the sound, a radio wave could be, say, thought of equivalent to a sound wave, which is kind of the hypothesis that I'm pushing. But once again, that's my hypothesis. And, I need to prove that, or the other side needs to prove their side about that it's made out of electromagnetic field. So we were spending a lot of time discussing that. And then we did get into by the prodding of Terry Ricker about, what's relativity. And, I gave my strange hypothesis, which I think I'm the only one that I know of who actually subscribes to this, except for maybe there was that Josephine guy who might have agreed with me that what he wrote was strictly correct, but what mainstreamers interpreted was completely wrong, and he's been wrong ever since. And then, so Einstein's wrong only because they're misinterpreting him. It's kind of weird thing. Then we ended there with David saying, what's the big deal? Relativity doesn't have any real super practical applications here. No one's going to be supporting it. So that's another interesting point of view. But once again, we are here to discuss things. Harry was making a couple points about, it's mainstream's never going to pay attention to us, and that's going to change. Although I did want to point out that Einstein seems to be a aberration. That he was definitely a dissident like us. In fact, he had his own little dissident group, just like we have here, and that's where he came up with all his crazy ideas about relativity. Wrote them all down in 1905 in a series of 5 papers. Now it did take 18 years. I mean, when he first published it, everyone thought he was crazy, and he was. But somehow, instead of being, completely ignored like the rest of us, somehow he managed to create this revolution in science. Somehow, I'm not quite not sure. I think he must have made a deal with the devil or something. But I think we've been the train has run off the rails since then, and that's why we're here to discuss things. And once again, I'm here to just provide an outlet for people who want to have at least somebody to talk to about their crazy theories, whatever they might happen to be. So that's what we're here. But CMPS is for. It's to encourage. Keep on thinking your independent thinking thoughts. Right? You might be wrong. You're probably wrong, but you might be right. It could be like. Well, don't be like Einstein and come up with something theory that's gets totally misinterpreted. Then you take over the entire world and turn physics into math and that sort of thing. But we're still out there. We're still trying. So that will do it for this week's episode of the Saturday Science Chat, and hope to see you all next week then. Okay, bye.